Thanks everyone for coming. My name is Andre. I'm engineer at Pinterest. And I'll be talking about how we do image similarity detection and a bit about clustering and doing it at scale, leveraging LSH and Tensorflow. And of course, over the Saprk platform. A few words about Pinterest. Pinterest is an online platform, primarily visual, that allows you to discover, sort, and organize your interests. And interests include things like travel, fashion, design, home decor, and so on. And we have a very powerful recommendation engine that surfaces relevant content based on your interest. We have over 200 million monthly very active global users, over 100 billion pins, 2 billion boards, and our recommendation engine across different surfaces such as home feed, search, related pins, and so on, surfaces over 10 billion recommendations daily. So the core of this talk is a system which we call near dupe, or sometimes alternatively far dupe, that detects and finds and clusters similar images. Not identical, but related. So I'll introduce the system first, then I'll talk about a bit clustering and what is LSH. And then the remainder of the talk will be going over different segments of the pipeline, starting at candidate generation, a bit of a deep dive into optimization techniques, and then more on the ML side of training a classifier to actually detect similar images. So first I'd like to show some pictures to show what exactly is a near dupe. So these are good examples of that. So you can see that they don't necessarily have to come even from the same image source. So the bottom right, you have two images of a kitchen that clearly come from a different photograph, but they are considered to be near or far duplicates. And the bottom left, both the train and the cars, they actually are against quite a bit of different background, just the primary subject is the same, and these are still considered to be near dupes. Different geometric distortions are also handled, as well as invariants such as mirror flip, rotation, cropping, all that fall within the domain of near dupes. And of course, not everything is near dupe. These two lamps are similar, but they are not similar enough to be considered near dupes. If you look at this at the spectrum, we have a classifier in the end that assigns a score, and you start with something that has only few related characteristics. If you look closely, there's a Korean overlay on top of pictures on the left. So some relation, but very light, all the way to almost a duplication on the right. And of course, this is very important for Pinterest platform because we want to show content that is distinct, that is engaging, and not duplicate in any way. I also want to say a few words about clustering. So fundamentally what we do is we actually don't just score individual pairs of images, but we try to partition the universe of images that we have into clusters. But that has actually a big problem because near-dupe relation is not an equivalence relation. So you can't really find equivalence classes. So the reason for this is not transitive relation. So you can kind of take a toy example and see that. Imagine you start with an image of a cat, and over 1,000 different iterations, little by little, you morph it into an image of a dog. And of course, those are very different classes. But at each iteration, the change is so small that it's well within the near-dupe distance. So how do you look at that sequence and partition it into classes? Is there a class of cat and class of a dog? Or maybe right in the middle, there's a class of cat-dog. It's not clear. So what we have to do is we have to approximate this approach. And the specific approach we take is we take a transitive closure, and then we take a greedy k-cut pass to make sure it's tractable from a computational point of view and also fairly accurate. That's all I wanted to say about clustering. The majority of the talk will be about candidate generation using LSH and candidate selection using a TensorFlow model. So a few words about LSH, or locality-sensitive hashing. It's a technique that is used to reduce dimensionality of high-dimensional data and preserve the pairwise distance of individual points. It's typically applied to make a space more computationally tractable for problems such as nearest neighbor search and so on. And in our case, the space is the visual embedding space. So embeddings in general is a technique to transform objects into a k-dimensional space which captures semantic similarity. And in case of images, similarity is also visual, not just semantic. So you may have heard of things like word2vec or fasttext or glove. Those are applied to textual things. In the image world, the architectures are such as VGG16 and Saprk provide to you representation of objects in an embedded space. So typically, you train a neural network, you chop off a few layers from the top, and that layer that is now surfaced is the one that's serving the embeddings. So for example, we use VGG16 and a layer called FC6. So a quick example of how you can map regional embedded space into LSH terms. So first, you have what we call random projections. So these are the black vectors in black. Of course, this is only two-dimensional space, but you can imagine a much higher dimensional space. And you select those ones. And then for each vector in red, those are the actual vectors representing objects, you look if they are on the same side with the projection, defined by the hyperplane of a projection vector. If it is, you issue a bit of 1. And if not, you issue a bit of 0. And you do that as many times as you'd like. The more bits you have, the more accurate mapping you will achieve. Unfortunately, even at that representation, you end up with a computationally non-tractable problem where we have large enough data sets, and at Pinterest we're dealing with billions and billions daily. So you actually have to group them in what's called LSH terms. And that's just an exercise of splitting a string of bits into distinct terms. So in this case, I selected 4 bits, and then I prepend a term index. That is necessary to ensure that you can treat your LSH terms as essentially a set or a bag, so you're not reliant on positioning. This is a bit of a toy example because we ended up with just 6 bits. In reality, you actually usually form, you take 12, 14, or 16 bits for the actual representation of random projections, and then you add an index, and you basically have integers at that point. So that's kind of the background sufficient for following the rest of the talk, which is focusing on how you can leverage Spark platform to actually do this efficiently and at scale. What we're looking at is a formulation such as this. And I'm using here RDDs, but it could be data set. In fact, it could be any kind of map. So you have an image ID, and you have a list of terms to describe this image ID. And what you'd like to achieve is for the image IDs in question, let's call them the query image IDs, you want to find top K similar images sorted by Jacquard overlap of those LSH terms. Essentially, this is a nearest neighbor formulation, and we'd like to make it tractable. So, for example, again, let's say object A is described by these LSH terms, B by 1, 3, 10, and C by 2 and 10, and more generically, some D I is described by a list of terms Tj, and we'd like to produce results that you see at the bottom. They're basically overlaps sorted by the amount of overlap. So, A has the most overlap with B, and a little bit less overlap with C. And of course, it's a symmetric relationship, so you see reverse pairs. If we were trying to sort of project this onto APIs and functional paradigm that Spark brings, you actually end up with a fairly elegant way of doing this, and I'll walk through this. So your inputs, you have 2 inputs. You have the index and you have the query set, and you can think of it as the set of entities, objects, or in this case, images that you like to search into, that's the index, and the set of objects that you're searching from. For example, all the images that users have interacted with on a specific day, and you'd like to find the similar items in the index. They're all represented in the same way, but contain different data. You can flat map and group it, and end up with it's basically an inverted index, a classical information retrieval construct. And the posting list is list of image IDs. You can join now an LSH term and flat map over queries. So it's flat mapping over one of those posting lists and grouping by, you end up with a list of posting lists. And then it just becomes a matter of counting your Jakarta overlaps in an efficient way. So, maybe I'll pause for a second to let you stare at this. But what I'd like to say is that this is an elegant representation that's kind of easy to follow, and it does provide the right answer. But the problem is this is orders of magnitude too slow compared to what we have in production and what our data sets requires to run with. And so I'd like to switch gears a little bit and go into a deep dive of some of the optimization techniques we've implemented to actually make it scalable. And some of them are fairly basic. I have some code, and some of them are a little bit more advanced. So the first thing, dictionary encoding. Your input data sets are most likely to contain very inefficient objects as they're stored in memory. Take strings, for example. Even just as simple as string IDs. And when you're dealing with billions of comparisons, and in fact, typically we compare daily billions of objects against millions of other objects, so that's naively a number with 15 zeros at the end. Every bit matters, every byte matters. And so Saprk has a very nice way of doing encoding entities with unique IDs. Either you can use zip with index or zip with unique IDs. These are two methods that are available to you. They have slightly different semantics, but they achieve the same goal. And then I have a simple test here at the bottom. What if you take 1,000 strings of 32 characters? That happens to be the length of IDs that we use at Pinterest. They're essentially MD5 hashes. And compare it to 1,000 integers. Well, it turns out it's 25x difference in memory utilization. It's more than you would expect because of inefficiency of storing strings, the object overhead, the byte alignments, and object headers, and so on. But that's a very significant price to pay for readability of the code. And so what we do is we actually map everything to the smallest possible primitives. The entire computation goes in this primitive space, and then at the end you kind of map back and get your results. So let's keep track of the wins. So here's 25x here. Verbal byte encoding, a classic technique for a inverted index compression. Essentially, you don't actually have to have a specific order in your posting list. In fact, for some information retrieval tasks, you can have a better performance if you sort everything. And so if you sort everything, then you can store, instead of the document ID representation, you can store its gap as an example before. And so on average, for very dense posting lists, which is the case if you have billions of items in your inverted index, you end up with very small gaps. So basically, you go from integer to a byte on average. So that's another 4x amortized. And so now 25x, another 4x. Now we have a 2 orders of magnitude reduction in memory. And of course, that's going to go a very long way in making sure your shuffle and everything is very efficient. In batch pipelines, a big portion of your time is actually not driven by total amount of data, but is driven by bottlenecks because of skewed data and certain partitions having more data and keyed in an efficient way. We have a very advanced way to map a regional embedding space into the LSH terms. It's a little bit more advanced than random projections I've talked about. And the main goal of this model is to ensure that the terms are as balanced as possible, but there's still going to be some imbalance for specific run day. And so one way to go around this is to partition your inverted index. There's a cost to it, and the cost is that for the query side of the computation, you'll have to copy your query for each of the partitions. But what you end up with is much more balanced index, such as you see here. Now the function here is just a module of document ID. You can be a little bit more creative and take the function that actually doesn't disrupt the variable byte encoding that I had on the previous slide. But essentially, the trade-off of much more balanced large index with a bit of overhead on the query side. So this gets, I would say, like very low level, but turns out it's worth it. So pairs are very convenient to work with in both Scala and Spark, but they're very inefficiently stored in the JVM because, again, you have byte alignment, you have object overhead, there's no such thing as a primitive pair. And it turns out if you pack them into a long, especially if you want to sort this, you are going to have a very significant improvement in runtime. So in this case, I do want to sort it by byte because the byte is the Jacquard overlap of the LSH terms. And so I'm packing it first. And you could see there's almost 20x improvement in the runtime of sorting and significant improvement in storage as well. So this one is a little bit hard to put specific code to it, so I'm just going to talk about it on a higher level. But essentially, there's a portion of your LSH computation that is very white in the sense that it spills a lot of things to disk through a shuffle. And while we have enough compute resources, we actually could run out of disk space, and we're talking about petabytes. So how do we go around this? And if you think about it sort of on a spectrum, on one side you have a real-time system. You have actual inverted index with LSH terms, and you query that at small batches or one at a time. That is also used at Pinterest. For real-time services. And on the other extreme, you have a complete batch system where you kind of get all your queries at the same time. You join them with the index, and you get all the answers at the same time. The problem is that you spill a lot to disk. And so in practicality, we found a middle ground to be the best working. So instead of doing all the queries at once, we partition our joint inverted index into slices. They're not exactly the same thing as classical Spark partitions. And we execute all one slice at a time, basically controlling for the shuffle spill to the disk. Usually, they're very, very large, about half a million to a million queries in a single slice. So it's still very batch-oriented, but we have the bound on this. So these are even sort of harder to describe in detail, so I'll go in a higher level of this. We took a page out of both data sets in Spark as well as classical relational databases and implemented code-based optimizer. So essentially, there are a lot of knobs that determine the behavior of LSH terms. Search over LSH terms. One of them is sort of very obvious, is the density of your original embedding space. Some of the spaces are very dense, so that for any particular point, you'll find a lot of nearest neighbors, and some are not so dense. And so what we do is when we run this pipeline, we actually sample our data, and we look at the density of it, and determine the runtime characteristics, and then set our parameters accordingly. It's a big win, and even bigger win in usability, because this is actually used across different teams in Pinterest, and so they don't have to set those knobs. Counting, neither Scala nor Java really provides high-performance libraries for counting, so we have to use much lower level libraries that basically are all around primitives and much denser, and it gives a pretty significant boost of performance. And finally, you kind of always benefit from hiding things from garbage collection, and so that it doesn't waste extra CPU cycles. Although what I've spoken about was was specific to images, this platform is actually used at Pinterest more generically. As you notice, none of this was actually specific to images, right? Other than the fact that the visual embedding that we generated came from a VGG16 neural network. So as long as you know how to transform your embedding to LSH terms, and as long as you have the slicing, which I've just spoken about, which kind of ensures that we can run on arbitrarily large data sets, this solution, this approach works well for any domain. And it's used for text, over word-to-vec embeddings and for another embedding that we have that's homegrown that kind of captures both text and the visual at the same time. So candidate generation via batch LSH is a very, very powerful way to sort of skip the pairwise comparison and get an efficient list of candidates with a high recall, but it's not going to have perfect precision because it's structured to be fast and sort of spit out as much data that's relevant as possible, but nothing to prune it. So for that reason, we have a candidate selection phase. It is actually run over exactly the same embeddings. It's essentially a transfer learning case. I have a simple architecture over on the right side. Couple of key points I want to point out about this is that we take an XOR of the Hamming bits of the visual embeddings because we don't want the neural network to relearn the fact that we're actually comparing images. We just want it to know which bits are important, which combination of the bits are important, and so on. We were very lucky to have a really large training set, thanks to the amount of data we have, so over 1 billion pairs. And I was personally surprised and found it exciting that the learning continued to happen without overfitting, even after seeing over 1 billion pairs. So the space is very complex. The types of images that are considered to be similar or not is rich. And then I have some parameters that I used to train the neural network. The training happened outside of Spark context, but inference happens inside Spark. And I think it's a really good fit. And the reason for this is that to get good performance, especially in the large neural networks, you want to vectorize as much as possible. And map partitions plus grouped gives you that control. So map partitions sends big batches and allows you to sort of process big batches at a time. But of course, sometimes the batches may be too big. And so you want to group it into exact size that you have a control over. And again, a little of a code snippet here that kind of shows this basic approach. With a neural network with over 10 million parameters, we can get 2 milliseconds per prediction. And the overarching theme here is that something like Tensorflow is really good at optimizing performance per core, and Spark is really good in distributing it in a distributed setting across multiple cores and machines. And so by combining these two approaches, you can get essentially the best of both worlds on inference side. You also want to avoid overheads that come with the large neural network. I think it's over 100 megabytes on disk, and so if you have to load it multiple times, that's actually going to significantly slow down your prediction. So session, which is a main paradigm in TensorFlow, is a thread-safe object, so you can load it only once using the lazy modifier. And so it's shared across multiple executors, multiple cores, and it lives through the entire lifetime of GVM, and just basically it's only thrown away after GVM exits. So in summary, I've talked about a pipeline to detect similar images and cluster them, and more broadly to work over embeddings that leverages the batch LSH implementation for candidate generation and does so at the very high scale of billions of comparisons a day. And then we leverage a neural network to prune the candidates and basically get down to the actual true positives via a candidate selection step. And then I haven't talked as much about two-pass transitive closure, but this is an approximation technique to actually partition an entire image universe into pseudo reflexive classes. So that's all I wanted to talk about today. I think it was about 5 minutes left, so I'll open up for questions.
Hang on, let me get the mic to you.
For your embeddings, did you use standard pre-trained with GG, or did you train it separately?
We started with a standard one, ImageNet one, but we fine-tuned it on Pinterest data because it actually has quite a bit of specifics to it, so it's not standard.
Hi. When we were talking to some of the Databricks guys about optimizations, they mentioned that data frames and data sets are far more optimal and have a lot of space savings. Have you guys looked into that instead of RDDs?
Yeah, so I took some time to rewrite this on data frames and data sets and found very little to no gain, and I think it's not because there's a problem with them, but because I've put so much sort of very specific shape-aware, data shape-aware optimizations here that those optimizations don't matter as much. So.
Hey, in order to create the LSH, what is the time and the space complexity? Like, does it increase the data size, or how much compute do you require?
So, I mean, in terms of data size, it most often decreases it, right? You start with, say, 4,096 floats, and you end up with 128 integers, so that's a huge decrease in space. In terms of the actual procedure to generate the terms, so the random projections is fairly straightforward. So it's just O of 1 per single projection, per single combination of projection and a vector. We use something a little bit more expensive that I think maybe we'll be talking about at a different talk, but it gives us much more balanced terms.
Hi. Is that 2 millisecond per prediction that you mentioned towards the end, is it like in the batch scenario averaged out, or it's like a real-time prediction?
This part, it's in the batch as well.
In the batch.
And that's why you can get such a low latency of a prediction, right. Because it's highly vectorized implementation.
I see. Okay. Is there a real-time scenario for prediction?
That is something we're actually actively looking at right now, and would leverage a lot of things here, for example, via Spark streaming.
Great. We have time for maybe 1 or 2 more questions. Question?
Yeah, can you clarify a little bit on the bitwise optimizations that we did, whether that was on the image IDs themselves, or was it on the binary encoding you got after the random projections?
Sorry, clarify on the...
So, for instance, with the first optimization you showed seemed to be on IDs. Is that the image IDs? So is this like a storage gain, or is it a computational gain?
It's both, because once you have to serialize 25x less data, that becomes a computation gain, but it's on image IDs, yes.
I see. So that binary ID you got from the random projections, that's left untouched?
Yeah, the random projections already come in short primitives, so that is already optimized. But the rest of the data shape that comes in may not be, and this is important. I would also point out this is not specific to batch LSH. In fact, it's a good idea to do anytime you have questions about fitting things in memory.
Is there time for one more question?
Okay, great. Thank you, everybody. Let's give a
Thank
round
you.
of applause for Andre.